Yeah, okay. So maybe let me actually say a few words because yeah, okay. So this is Ravi, as you guys probably already know. And Ravi has been doing lots of very interesting things in the foundations of physics. And today he's going to tell us about. I think I heard a shorter version of this talk at some point in lessons, maybe. But yeah, he's going to talk about this non-classicality of indefinite causal order.
Okay, cool. Thank you. Thanks, Atul, for the invitation. Um, I'm quite happy to speak at Mini Quick, as you called it, informally. Yeah, I'm still using my Brussels account actually to do this talk. So, yeah, formally I'm still at Quick, it seems. Okay, so yeah, so I'm gonna share some work. It's joint work with Ognian Oreshkov. And here's a, like, if you look at this, can you see my cursor? You can see my cursor, right? Yeah. Okay. So
Yeah.
okay. So if you look at this preprint, the shorter version is this 2411 one. So this will give you an executive summary of the highlights of the longer paper, which is this one. So yeah, depending on how deep you want to get into it, you can pick either version to look at. And the central sort of thing that we're trying to address in this work is the question of what does it mean to say that you're witnessing some sort of non-classical behavior when you're living in a world with indefinite causal order. Like, what does it even mean to say that that there is such a thing as non-classicality in that world? Okay, I'll try to motivate this question a bit better, like where it comes from. So I'm going to not assume too much and introduce everything. So if you have questions, I think we have enough time. So in case something is not clear during the talk, you can ask for clarification. Okay. Okay. So the first thing. So when we use the word quantum, when we say quantum, that usually entails that we are referring to something that's not classical, some notion of non-classicality. Now, this can be various different things depending on what you care about. It might be superpositions, it may be incompatibility of measurements, it may be correlations, non-locality, things like that. So it can be very many different things depending on what you work on. If you do quantum optics, you look at Wigner negativity maybe. So non-classicality can mean many different things. What we are going to focus on in this talk is those notions of non-classicality that fall under what you might call probabilistic notions, in the sense that these notions are applicable to observed experimental statistics, observed quantum probabilities. Okay, so those are the notions that I'm referring to when I use the word non-classicality here. So there are three observations one can make about non-classicality. So first, that well, before we get to non-classicality, first about quantum theory itself. So first is that quantum theory is intrinsically probabilistic. So this is what the Bond rule tells you. Something called Gleason's theorem, which justifies it, also sort of suggests this. So given the structure of measurements, you know that there's no way to assign deterministic states in quantum theory. So it's intrinsically probabilistic. But we know that these probabilities are not classical. And how do we know that? One device independent way that we know that is because these probabilities can violate Bell inequalities. So they exhibit this feature called Bell non-locality for parties that are not signaling to each other. And we also know that actually probabilities can, in fact, be more non-classical than what is allowed in quantum theory. So there are many ways to be non-classical, including post-quantum ways, right? Conceptually, in the conceptual space of non-classical correlations, there can be correlations that are not quantum, but they're still they're quite non-classical. Okay, so keep in mind these three observations as we go along, because similar questions will come up when we talk about indefinite causal order. Okay, so the general question is, one might ask, okay, I said probabilistic notions of non-classicality, but what does it even mean to say that a probability is non-classical? I mean, probability is just non-negative numbers that add up to one. So, I mean, what's non-classical about some real numbers? Like, So of course, like there's nothing non-classical about some numbers. It's the assumptions under which those probabilities are obtained that makes them non-classical. Okay, so what does this mean? So for example, if you're looking at Bell inequalities or Bell scenarios, so the more contemporary way of thinking about these is in terms of these causal models. So if you're given a directed acyclic graph, and if you require something called the classical Markov condition, don't worry about what that means. In traditional terms, it's often like the existence of a local hidden variable model. So basically, the point is that the structure of this DAG, the way nodes are connected to each other, implies certain constraints on the observed statistics, and those constraints are called Bell inequalities. And when you violate those inequalities, you're essentially proving that this DAG could not generate those correlations using only classical random variables. Okay, that you will need some entangled state and some quantum measurements to actually do it. So Bell inequality violation certifies non-classicality in this sense. Now, so going further on, so this is a classic picture of this is from this review on Bell non-locality of you have the local polytope, the set of correlations you can generate using classical shared randomness. That's L. You have the quantum set, which is convex but not a polytope, and that's Q, which contains the classical set. And then you have the no signaling set, which is a polytope and which surrounds the quantum set, right? So, and these are three different sets of correlations. You have classical, quantum, and then things that can be more non-classical than quantum. So this is just
for clarity. Sorry, Ravi, for the interruption, but just for clarity, could you explain what the points in this diagram are? Like what a single point in this diagram?
So the points, I will come to this, but these points are essentially correlations. These are probabilities of outcomes given settings that many parties can observe. Okay, so it's a probability vector. Imagine that these points here are points in some real vector space where each point is a list of probabilities, a vector of probabilities for different settings. Anyway, so I mean, I'll make this more precise as we go on. This is just to give a sketch of, just to recall some things you may already know before I go on to indefinite causal order and stuff. Okay, because if you reason with in analogy with Bell, I think a lot of what I'll say will make sense. So that's why I'm kind of doing this quick overview, so that people who know about it might maybe situate with the new stuff I say in the context of Bell scenarios as well. Okay.
Right.
Okay. So so far I said, okay, Bell is an assessment of non-classicality when you're given a DAG. So a DAG is a causal structure. So if you're given a causal structure that constrains the kinds of correlations you can generate, and then those correlations may admit classical explanations, they may not admit classical explanations, which means you cannot generate them with classical random variables, in which case maybe they require quantum states, or maybe you can't generate them even with quantum stuff, in which case they require PR boxes or really non-classical things. But what does it mean to say that we want to talk about non-classical probabilities without global causal assumptions? So this is kind of the challenge we're dealing with. We're dealing with a situation where we're not assuming a network structure. So no network structure is assumed. So there is no DAG. There's no underlying DAG that we can appeal to. If we're really trying to relax causality, like the most extreme way to relax causality is to say that, okay, I don't assume any global sort of causal order between parties. Okay, so in particular, not assuming a global causal order means that I cannot put them, assign them some vertices and draw like arrows, causal arrows between them, such that the causal structure is a directed acyclic graph. Okay, so this is what we're dealing with. That's the central question. And so here's an outline of the talk of how we're going to approach this question. Okay, so I'm going to try to give you a sketch of what the setup is, what the framework is within which we are working. Like just like a Bell scenario describes a particular setup in which you describe things. Here I'll describe the setup that we are working with. Then I will, in that setup, I'll talk about these things called causal inequality violations, which are which are device-independent witnesses of indefinite causal order. So they're expressed in terms of observed probabilities, and if you see such probabilities, you can kind of certify that parties are not in some global causal order. So you cannot assign a DAG to them in some sense. But then we see that I'll point out how although you can violate causal inequalities with by receiving quantum systems, it's actually not the case that these causal inequality violations are some intrinsically quantum things. So you can have classical versions of causal inequality violations, and so that kind of raises the question that, well, I mean, if you can violate causal inequalities in a completely classical theory, then what's so non-classical about that? How do I know that the indefinite causal order I'm seeing, assuming that I assessed it using some observed probabilities, how do I know that that's actually coming from some quantum thing, like some quantum structure, space-time, whatever, rather than, let's say, just classical closed-time-like curves or something like that? Okay, so that's what I'll point out, that there's this tension for causal inequality violations. They're not always non-classical. And then a way out of that will be our proposal for a notion of non-classicality for correlations in the presence of indefinite causal order. And the name that we give to this notion is antinomicity. Okay, and the rest of the talk will be trying to explain to you some properties of this notion. It's a device-independent notion. So again, it's expressed at the level of correlations. And I'll try to also maybe give you an intuition or try to justify why actually antinomicity is, in some sense, the rigorous generalization of Bell to a situation with indefinite causal order. Okay, in the sense of certifying non-classicality. So, okay. So let's begin. So here's the setup. So we'll work within this sort of a general operational paradigm where we imagine that there are n parties, so n labs. So this box is the lab where it says local intervention. Okay, and these are closed labs except for an input system that a lab can receive and an output system that the lab can send out. Okay, so this is all the free input. This is the input and the output systems are the interface of the lab to the rest of the world. Okay, and the rest of the world can of course include other labs. So I'll be labeling the labs by the index K here. But it also includes like things that are outside of all of these other labs, right? So that's what we call the environment. So and the environment is what surrounds all the labs. None of the labs actually control the environment. The environment is autonomous from the labs. So they don't control the environment. They only control what's happening inside their labs. Okay. So this environment, for example, could be a causal environment. For example, just Minkowski spacetime, which means that they're in some definite causal order. Or it could be something more exotic. We don't know what it is. So, and we're not going to assume too much about it. What we're going to talk about essentially is what these parties can see if they play some sort of game. What kinds of behavior can these parties see? Okay, and when I say a game, it means that imagine that there's some referee that these parties receive some questions, and they're supposed to respond with some answers, just like in a Bell scenario. So
Hi.
Yeah.
Ravi, just one quick question over here. Is this, when you talk about the environment, you talk about a one global environment, or for there is an environment corresponding to each of these individual boxes that you are talking about?
There's one global environment for all the labs. Yeah.
Okay.
So I'm not drawing the full picture here. I just do it for one lab, but you can imagine like n slots in like a one Coombe kind of picture. Like it's like, I don't know how to express this, but yeah, imagine n copies of this lab and like they're all sharing one environment. Yeah.
Yeah. So I have another small question, Ravi, just a clarification.
Yeah.
So this local intervention part, we are assuming that everything is quantum mechanics inside somehow. Is that
not yet? Not yet.
Okay.
This is
do we
for now.
that that's... Sorry, go ahead.
No, finish. The
Oh,
question.
I was my second question was that is there like a causal order in say, for example, the input system is first received, then the question is asked, then the answer is given.
Yes.
Do we assume that?
Yeah. Yes, I should say that. Yes. So the assumptions we are making on the lab is that, okay, there's some theory that describes the systems that are received by the lab and systems that are sent out by the lab, and that theory also describes what you can do to the systems. But at the moment, we're not assuming what this theory is. It could be quantum theory, it could be classical theory, it could be some generalized probabilistic theory. We don't know what it is. At the moment, I'm just describing the skeleton of the framework. I'm going to put some meat onto it, which means some sort of theory as we go on. Okay, the minimal assumption we are actually making, yes, that was a good point that you made, that the input system that each party receives causally precedes the output system that it sends out. So there is definite causal order inside the lab. So that is an important point, that inside the lab, causal order is well defined. There is no ambiguity about what comes, like you can draw DAGs for all the events inside the labs. What you cannot draw DAGs between is events that belong to different labs. Okay, so there's no assumption of a global causal order between different labs, but within each lab, if you only look at variables inside that lab, you can put them in a definite causal order. In particular, the input system is causally before the output system. Okay, what we need basically is just this minimal causal assumption that the input arrives before the output is sent out. Okay, for each party.
Great, thanks.
Is that okay? So yeah, so everything I'll say about when I say indefinite causal order, it's really about causal order between the labs. It's not about causal order inside the labs. Inside each lab, causal order is definite. Okay. Okay. So one way to sort of fill in what's going on in this general operational paradigm is what's called the process matrix framework. So this is due to Ryshkov, Costa, and Bruckner. And here we assume that quantum theory holds inside each lab. Okay, so inside each lab, you can receive a quantum system. It has some associated Hilbert space, HIK. You can send out a quantum system with some associated Hilbert space, HOK. And on the input system, you can implement arbitrary quantum instruments. Okay, so here I'm just labeling this is basically the Choi matrix for the channel you might implement. So AK labels the setting and XK labels the outcomes. So like, the AK is the instrument that you are implementing, and XK is the different sort of CP maps that belong, labels the different CP maps of that instrument. Okay, so if there are students or people who haven't seen this stuff before, don't worry about like the details of the mathematical structure of this. For now, I just want you to focus on the fact that you're doing some quantum stuff inside the lab, and you're sending out things. There's causal order, and then the thing is that you want to describe this environment. You want to give some description for what the environment is. Okay, and the way we make a minimal assumption about the environment, we make the assumption that the environment. So we know the mathematical structure of these things because this is standard quantum theory. We know what quantum instruments look like. We know what quantum systems look like. So we know all of that. What we don't know, at least until this process matrix framework, was what is this environment, how to model the environment. Okay, and so the process matrix framework is the claim that the environment can be modeled by an object called the process matrix, and this object is basically a huge matrix over the tensor product of all the inputs and output spaces of all of the parties. Again, details are not that important. The more important thing right now is to recognize that this object, it combines with the local interventions of the parties, like in this fashion. So in a fashion that resembles kind of the bond rule. Okay, but W is supposed to represent. So intuitively, it represents a channel from the output systems of the parties to the input systems. Okay, so it's, in some sense, if you have a channel from the Alice's output to Bob's input, that describes like communication from Alice to Bob, for example, right? But if you have a channel from Alice's output to Bob's input and Bob's output to Alice's input, that describes two-way sort of communication, which may be non-causal. Okay, especially if it's happening at the same time. So the process matrix can represent those kinds of things as well. So is the most general description of a channel from the output systems of the labs to the input systems in such a way that the observed probabilities, so these conditional distribution of outcomes given settings for the n parties, are given by this trace rule, and these are non-negative and normalized for all settings. Okay, those are the only constraints. We just want to make sure that the probabilities make sense for arbitrary choices of, so the important thing is that these instruments can be arbitrary. Each party is free to choose what it does in the lab. So there's no constraint on what each party can do inside its lab. It can do whatever quantum theory allows. Okay, so under a variation over these local instruments, you should always get sensible probabilities given a process matrix. And this condition is called logical consistency in the framework. Okay, it's just the idea that the probabilities always add up. There's no subnormalization, there's no supernormalization, there's no negativity. Everything makes sense as like regular probabilities. Okay, that's what at the moment take logical consistency to mean just that probabilities make sense. Okay, that's what this W ensures. They make sense under arbitrary interventions. That's important that you do not restrict what the parties can do. Okay, so that's the first way of filling in this operational paradigm. Another way to fill in this operational paradigm is to say, okay, let's imagine another world in which the labs are restricted to just doing classical stuff. So now the labs receive a classical system. So IK is just some classical random variable in which you can encode the state of the incoming system. OK is the random variable that encodes the state of the outgoing system. And and so you receive classical systems, you send out classical systems, and you can do arbitrary stochastic operations on what you receive. So classical stochastic operations. So you receive some setting AK depending on the setting and the input system you've received. You do something to that input system, which is described by this guy, and you send out some output system, and you report some outcome, right? Like some XK. So this is the classical version of a quantum instrument. And again, we have to describe the most general channel from the outputs of the parties to their inputs. Okay, this channel kind of essentially describes how the parties communicate, because remember, the only way they can communicate is by receiving and sending systems. So if you describe how the systems they receive depend on the systems they send out, you've described the communication. Okay, that's what this thing is. This is a classical process. It's a conditional probability distribution over the inputs of the parties given the outputs they send out. Okay, outgoing systems they send out. And again, this is subject to logical consistency, which is that the probabilities you generate. So this is the expression for how the probabilities are obtained. So these are the local instruments. Remember, these were under tensor product earlier in the process matrix language. Here we can just write them as a product of these guys. And P of I given O represents the channel from the outputs of the parties to their inputs. The important thing is that this channel is not arbitrary. So it's not an arbitrary conditional distribution. So this when I say logical consistency, the requirement that these probabilities are non-negative and normalized for all settings puts restrictions on what this P of I given O can be. Okay, and so it cannot be arbitrary. It has to be such that these probabilities add up, because you can write down examples of this where probabilities will not add up and you will get paradoxes and stuff like that. So this has to have, essentially it's the same constraints we impose in the quantum case. Now we're imposing it in the classical case. And so this is the framework. Okay, so this framework can generate correlations according to this sort of probability rule. And again, this paper sort of motivates this framework axiomatically from first principles without actually appealing to the process matrix framework. And then in the paper itself, you will see that there is a theorem where they show that this framework is equivalent to the diagonal limit of the process matrix framework. So if you, in the process matrix framework, if you require that if you fix the bases in which, for each party, the local basis in which it receives systems and the basis in which it sends out systems, and everything like is diagonal in that big sort of product basis for your process matrix is diagonal in particular, that limit, so in this paper, they've proved that limit is the same as the classical process framework. Okay, so it's a theorem. It's not. They don't derive the classical process framework from the process matrix framework. They derive it axiomatically, and then they prove that it's equivalent to the diagonal limit of the process matrix framework. Okay, so this distinction is important to keep in mind. That it's okay. Question?
Sorry, Ravi, I have two small things I wanted to quickly check. So one thing is that just to double check, the logical consistency condition on P, capital P I given O is derived as identically to how it was derived in the quantum case, namely that you impose that the probabilities are normalized and positive or non-negative. Right?
Yes.
That's how it. Okay.
Yeah.
And the other thing I wanted to quickly check was why do we need this limiting procedure in the theorem statement? I would have imagined the statement would be much cleaner, like naively, right? That I would have thought that if it's diagonal, the process matrix, then it's equivalent to this classical process framework. But you're somehow saying that there's a limiting procedure involved. Can you explain a bit why that is happening? Is there like an easy way to understand what's going on there, or?
I mean, the easy way to understand is just that if you fix the bases, then you can write down everything in like in a diagonal way, right? Like if you're not allowed to sort of essentially manipulate any
Right.
superpositions, basically. That's the
Right.
easy
So
way
what
to
is the
understand.
limiting procedure? What is the limit over? I mean, I'm getting a little bit lost. I thought it would be like
What
exact, right? I don't understand where the limiting
what
procedure is.
there's no limiting procedure. Like I don't know
Ah,
what did you understand by limiting procedure? Like, what was that?
I think I misunderstood. Sorry. So I thought the theorem statement you mentioned was that in the limit that it is diagonal, the process matrix
The
that.
limit. I didn't use the word limit in a very technical sense. I just meant that if you assume everything is diagonal, it's the same as the classical process
Ah,
framework.
okay. Sorry. I thought
There's
there was
no.
like some
I
continuity concern.
No,
Okay.
no,
Sorry.
no.
Sorry.
It was not. It was not a
Sorry.
technical use of the word limit. Yeah.
Sorry. Okay. Thanks.
You took the word limit to its technical limits. But anyway, okay. So okay. So that's the second way of. So first way was process matrix framework. Second is classical process framework, and the third. So again, this is again from this paper, but I want to distinguish three different things rather than two different frameworks for my purposes. And the third framework I'll call the process function framework. Okay, and I'll call it this because this is qualitatively, in some sense, distinct from what classical process framework is doing. And here essentially what you have is the same restriction on what the parties can do locally, that they just do stochastic operations. So everything is classical in local labs, so nothing changes about that. But in the first instance, you require that the channel from the outputs of the parties to their inputs, you look at deterministic channels. You look at functions from outputs of the parties to their inputs. And those functions, for example, you can represent them with some delta function from that maps the outputs to the inputs. And so you look at all possible functions that give you sensible probabilities according to this rule. And then you take a convex hull over that. You allow for convex mixtures of those guys. Okay, so this is a convex mixture of what things you might call process functions. So when this thing is a function, then it's called, instead of a classical process, I'll call it a process function. And if you take a convex hull over process functions, that's the most general description of the environment in the process function framework. And now the important thing is, the reason I'm making this distinction is because this convex hull over process functions is a strict subset of classical processes, of what's called the classical process framework. Okay, it doesn't cover, the convex hull actually doesn't cover all classical processes. It's a strict subset. Okay, and this is an important thing to keep in mind. That's why I'm calling it the process function framework, because it has a nice notion of the nice thing about this framework is that it has a notion of preservation of logical consistency under sort of probabilistic mixtures, that kind of thing. Because here I can decompose any environment that you give me. I can always decompose it into a probabilistic mixture over process functions. This property is not true for an arbitrary classical process. For an arbitrary classical process, if I do a decomposition over functions from outputs to inputs, then in general, I will require some non-zero weight on functions that are not process functions, that can give me probabilities that don't add up. I don't see it on average that the probabilities don't add up, but on there will be some functions in the fine-grained picture where probabilities will not add up, and which corresponds to essentially time travel kind of paradoxes. Okay, this will come up again later, so I will explain this with more concrete examples later. But I just wanted to state that there are three different frameworks that we're looking at: process matrix, classical process, the diagonal limit of the process matrix framework, and the process function framework. And the process function framework, again, another way to think of it is you take the diagonal limit and then you require that the diagonal entries of the process matrix are only zeros and ones, so that you don't have any probabilities there. And then you take a convex hull over those things, which again is not the same
Ravi,
as, yeah.
so what is
Yeah.
omega here?
Omega
Delta
is what
function?
omega. So I've labeled it by lambda just because I wanted to later on talk about this sort of mixture. But omega is what I'm calling a process function. It's a function from the outputs of the parties to their inputs. I haven't specified constraints on it, but basically the constraints on it, the explicit constraints on it, follow from requiring that this expression for the observed probabilities makes sense for arbitrary choices of these conditional distributions for these stochastic operations. Okay.
So do I understand
also-
that this omega restricts the convex hull to be larger than this delta function convex mixture?
Yeah,
So
small.
is omega restricting in the nature that the convex hull is smaller,
Yes, the convex
or
hull is
other way,
smaller.
I think. So I'm
Yeah.
confused. So,
Okay. Yeah.
so convex hull, you said that could you say again what was the convex hull? Is it smaller or bigger?
Okay, I will say this. I will say it in 3 steps so that it's kind of again maybe clear. Maybe I spoke too much and it was not clear. The first thing, we look at deterministic channels from outputs to the inputs. So when I say deterministic channel, it will describe some function of the outputs that gives me exactly what the input that the parties receive is, and that's this function omega. Okay, here I'm labeling it by lambda. A particular instance of omega is labeled by omega lambda. Okay, and then
Yeah.
And then I'm saying that this is not an arbitrary function. This cannot be an arbitrary function from outputs to inputs. It has some constraints on it. In particular, there's something called the unique fixed point condition, but you don't have to worry about it right now. That condition is essentially a consequence of the fact that I require these probabilities, P of X given A, to make sense when I plug in arbitrary interventions. So arbitrary local stochastic operations. Okay, so that restricts the set of classical functions from outputs to inputs, this constraint. And then I allow a convex hull over these restricted classical channels.
Okay.
Does that make sense? And then
Yeah,
so this is what this is. And then I'm saying that the thing that I just described, the set of classical processes that appear here in the process function framework, is a strict subset of the set of classical processes that appear in this framework, where I only require that the outputs, so the probabilistic channel from the outputs to the inputs, should give me sensible probabilities, sensible correlations under arbitrary local stochastic operations. So naively, one might think that these two things should be the same. But what I'm trying to say is they're not the same. It's known that they're not the same, that this is a bigger set than this set.
So is this because of the choices of omega imposed by this conditional probability Px given A?
Say that again?
So it feels to me that omega is restricted by this big equation Px vector
Yes,
given A
yes,
vector.
exactly.
So
So this equation should make sense as you vary over the local interventions. That's the constraint. So you can choose arbitrary, you can plug in arbitrary things here, and you should still get normalized probabilities and non-negative. I mean, they'll always be non-negative. They should be normalized for all settings. That's the constraint. So that's where the constraint on omega comes from.
So will it be true that if omega was all functions from output to input, then the convex hull will match with Pi given O?
Yeah. Yeah, in that case, actually the convex hull will be actually even bigger than this, because you're not even requiring logical consistency. So you can actually achieve any arbitrary distribution from outputs to inputs, because even this is restricted. This is not an arbitrary conditional distribution, because here also there's a constraint coming from this equation.
This looks very strange actually, because Pi given O was also restricted by this big equation.
Yeah, exactly. So basically, what I'm trying to say is that, yeah, this intuition you might have is that if I just take the convex hull of deterministic thing, I'll get the classical processes. That's not true in this framework. That's the weird thing.
I see. Thanks.
Yeah, I'll give you concrete examples, like single party examples soon. So just to kind of clarify what I'm saying. Okay. Okay. Here's the example. So actually, this is the example.
Sorry. So before you go on, one small clarification question. So when you're writing Pi, so capital P, I given O, that does not seem to depend on lambda explicitly.
Yes,
while
it
the
doesn't.
right-hand side that seems to depend on lambda. Is it just notation, or is it something?
Yeah, it's because I badly wrote it. Like, yeah, okay. It's this P of I given O is not the most general distribution, right? It's just actually meant to be just this process function. So you can put a superscript lambda on it just to say that it's this, and then I take a convex hull over these things with lambdas on top, and that's this.
I see. So the condition that you're requiring,
it's bad notation. So I should admit that it's bad notation. Yeah.
I see. So the condition is that regardless of what P lambda distribution I use, Px given A, on the bottom left should be consistent, like should be a valid probability, regardless of what P lambda is and regardless of what the local processes are, right?
Yes, exactly. Yeah. So this can be arbitrary. This P lambda is an arbitrary distribution. There's no constraint on this. This is an arbitrary convex combination.
Right, right.
Yeah. The only constraint is on what these functions are. Yeah.
So is it enough to just put those constraints on those functions individually, or do you get a stronger condition if you impose the constraint for all P lambda?
I mean, the constraint is true for all lambdas, right? So, and is that what you were asking? Like the only functions we're looking at are the ones that satisfy the constraints, and I'm labeling them by lambda. And I allow convex mixtures over them.
I see. So okay. So strictly speaking, the condition that you want is that the equation that you wrote on the left hand side should be true for every delta I omega lambda. Or is that the way to think about it?
So, well, I mean, for each delta I omega lambda O, when I put that here, this equation should give me valid probabilities no matter what interventions I plug in. Okay. So for each one, I allow arbitrary interventions, and I make sure that for any intervention I get like valid probabilities.
Right. Yeah. I would just ask. Yeah. Okay. It's fine. I'll bother you later. I think it's good enough for me.
Okay. Because I haven't even. Yeah.
I also have a question. Sorry to interrupt again. So
hi, Ian.
Hi. So in this P of I given O, so you already assume that this is a conditional probability, right? When you write P I given O.
Yes. Yeah.
So
yes.
Is this is it clear that these are the only P I given O's which could satisfy this logical consistency? Or I might have...
So it's a necessary. There is a necessary and sufficient characterization of this. Yes. So the ones we're looking at are the ones. So this is basically the. Actually, if I show you the example, it'll make more sense. Can I show you the example, and then we come back to the discussion? You can just hold on to the question, and then we see. So here's an example. So this is the simplest example. You have a single party. Okay. So single party. No, you don't have n parties anymore. There's this environment. The environment is an identity channel. It's a classical party. It only does classical instruments. Okay. It receives a bit I. It sends out a bit O. Okay. The environment just passes the bit back to the input of the party. Okay. Now the party, according to our framework, what I was saying was that for arbitrary interventions, the probability should make sense, right? That there should be no paradoxes essentially. Okay. But if I say arbitrary interventions, then one intervention I can do is to just flip the bit I receive from the environment, right? So if I receive the bit 0, I flip it and I send out a bit 1. And if the environment sends the 1 back to the input, it means that there's a conflict with the value I input earlier. So there's a logical contradiction. So formally, this will correspond to identifying a local intervention, which is basically the not operation inside the lab, for which your candidate function from the output to the input fails to give you probabilities that add up to 1. Actually, the probabilities are just 0 because that's basically this is what people call the grandfather antinomy. This is a bit like going back in time and killing your ancestors. So how did you come to be if that? So that is just the digital version of that paradox. Yeah. So this is often called the grandfather antinomy. So if omega is the identity and if the party flips the inputs, there's no fixed point. So when I use the word fixed point, that's just saying that there's no input that provides a valid solution to this loop. Does that make sense? Like this is an example of a thing that is not a process function, of a channel from output to input that's not a valid process function. So I will not allow a convex mixture over that in this description.
Excuse me.
Yeah.
Question. So here in this example, are all the 3 polytopes the same for one party? Or could it be that
which polytopes? Because
of the
you mean the correlations?
probabilities? Yeah,
the correlations, like these guys.
For a single party, yeah.
Yeah, so for a single party, let me think. You have classical quantum is the same. Yes. Yeah, I don't think you will have any gap between classical and quantum in terms of, because you can do arbitrary things. So if you can only do causal things. So you cannot put a gap between classical and quantum, and because you require logical consistency, so you cannot there's no way to do that. But in general, the set of correlations is larger than what you can do classically and quantumly. Because the thing I said was that you can do arbitrary interventions here, right? So you can also say that, okay, no, I'm working in a theory where I restrict the interventions. Like in time travel movies, they often they just create a situation where you just fine tune the situation that you can never actually do this thing so that's kind of like putting restriction on what you can do inside the lab, and so that the paradox never happens kind of situation. So, but that's not the kinds of theories we're looking at. We're looking at the ones where you can do arbitrary interventions, and they should not allow paradoxes. So under that constraint, classical and quantum are the same because they only give you causal stuff when correlations that don't violate causal inequality. That's a causal stuff. That's what I mean.
Hi, Ravi. This is Indrani. One comment over here that the setup that you are describing over here, it looks very familiar with the Deutsch-CTC model. So I don't know what is the intuition, because in the Deutsch-CTC model, we have this one causality respecting qubit and another is causality violating qubit. So CTC region and CR region. So, and they have this kind of a loop, and that fixed point equation, they call it a kinematic equations, and that fixed point equations takes care of this grandfather paradox. So what you are here?
Yeah, so it's so actually it's not directly related to that, but the intuition is that in the Deutsch model, if you want to think of it this way, it's at least in the classical version of the Deutsch model, you can always think of it as saying that I will take an equal mixture over the identity. Wait, I don't want to say something wrong, but it's basically the way you avoid a paradox is by kind of taking a random mixture of 0 and 1 at the end, because that's what avoids the paradox. If you take a random mixture, then on average you get a fixed point, basically, or one fixed point. Because the noise kind of avoids the paradox. That's the intuition there. But the thing is, that's not what so when I say this process function stuff, that excludes those kinds of possibilities where you use noise to hide the paradox. You're not allowed to do that in this picture. So that's what I'm trying to get at, because this is not a valid process function in that sense. So I cannot even take a convex mixture over this for this framework.
So also, Ravi, so it feels like that omega is fixed here, but you are considering all the functions. So when you write the expression, should there be some integration over omega other than lambda?
So this is the lambda thing that I wrote down, because basically we're looking at discrete things, like at least the picture that I've written down is like discrete systems. So you can just write down a sum. It's fine. I think it's not a problem, because you just need to represent like maps from O to I. And there's
so omega lambda is a single variable. It's not like omega is variable and lambda is variable.
Yeah. So you can write down omega as an n tuple of functions, right? So for each party, so I wrote it like this, but it's basically I1 is a function of O1, O2, O3, On in general, right? So there's some omega 1 that describes how the other party's outputs map to this party's input. And there's an omega 2 that describes how other parties' outputs map to the second party's input, and so on. So omega can be written as omega 1, omega 2 up to omega n, where each. So you can write any function like that, right?
Oh, I'm just concerned that the integration of summation should be over omega if omega is varying.
Yeah, so this lambda is labeling the omegas, no? So this is over omega, like the thing I've written down.
I see.
You see, like the lambda was supposed to just allow me to do that. That's why I labeled them with lambda.
Okay.
Yeah. So I wanted to also mention the second one, which is called the information antinomy. So again, here, this is another example of something, another way to see the paradox. So if you have, imagine you just do the identity channel. You just send the bit you receive forward into the future, right? And then the environment sends it back to your past. So this here, it might look like a priori there's no paradox, but the paradox here is that it's an initialization problem, because there's no way to fix the value of the input bit. It could be 0. That's a valid solution. It could be 1. That's also valid. It could be anything. Like, there's no laws of physics that tell you what the value of the input bit is in this situation. Okay. So the way that it formally reflects this problem in our in this process function kind of language is that the distribution P of x given A, it'll end up being super normalized. So you have too many fixed points. Here you had 0 fixed points. There was no solutions. Here you have 2 solutions, which is the maximum number of possible solutions if you had bits. Okay. And if I took a uniform mixture of the two, if I took half probability this, half probability this kind of thing, then on average, it'll look like I have 1 fixed point. But underlying, there's always a paradox. You see, like this kind of the intuition for the Deutsch, kind of like to go back to that kind of thing. But for our purposes, the point is that this is not a valid process function because I can always pick local interventions that will make my observed probabilities not add up. Okay. And I only allow, for the process function framework, I only allow a mixture over things that are process functions.
Ravi, so can you explain point B a little bit better? Well, not better, maybe. Can you repeat it? Because I didn't fully understand why having multiple solutions. Sorry, can you hear me?
Yeah.
Sorry, I didn't fully understand what the issue is if you have multiple solutions. In particular, I didn't see how it's related to the normalization issue.
Okay. Let me give you an intuitive example of what multiple solutions means. So if you go back in time and I think it's Shakespeare's birthday. In any case, if you go back in time and give Shakespeare all his plays before he ever wrote them, and then the question becomes who wrote the plays? Okay, like why did the plays take the shape that they took in your hands? If they took the shape they took in your hands, is because you send them plays, right? Like they could be anything. They didn't have to take the form that they take today. So it's a paradox in that sense of initialization problem. So I could have, so this is the intuitive kind of pop science answer to why that's still a paradox. It's an initialization problem, and the formal answer is that in the left-hand side case, the grandfather antinomy is the case where these probabilities will add up to 0 for some settings. That's what I'm trying to say. No matter what you do, okay. That's basically because there's no solution, so they will add up to 0. Like I haven't written it down explicitly, but that's what it means. And for this case, when I plug in these interventions, the probabilities will add up to more than 1. They'll add up to 2. That formally is equivalent to saying there are 2 sort of solutions. Okay. Again, I'm not rigorously proving this, but I'm just trying to tell you that this.
Yeah.
Okay. And the thing is, if you're allowing free interventions, if I'm not restricting what the party can do inside the lab, it can create this paradox or that paradox. It's free to create either paradox actually. So these two paradoxes actually are formally equivalent under free interventions. So if you don't restrict the interventions of the party, so that's in this paper. You should check this paper if you're interested in understanding like this stuff better, because this paper does a much better job than what I'm doing of explaining this inconsistency stuff, because it's completely about process functions, and it shows you the equivalence between these two kinds of antinomies in the general case of n parties. So I just illustrated it for one party. Yeah. Okay.
Yeah. Thank you.
Okay.
I have a question. It's like, won't that be a problem for like every invertible channel kind of stuff? Like, for example, let's say you have some input, and then in the local intervention, you get some output, and the P matrix then again inverts that output to the input. Then like again, like there is some initialization problem. So like it is saying kind of like inversion cannot exist if we want to be logically consistent.
Yeah. So when you say inversion, that's just like I mean, this is like causal in, like, the thing is you have to think of it causally, right? Like I said, the input is before the output in each lab, right? So you're saying that the future signals back to the input, right? Does that make sense? What I'm saying?
Yeah.
No, it's not that inversions can't exist. It's just that those that create paradoxes are not valid process functions. Like they can
temporal
exist
inversion cannot exist. Like temporal inversion cannot exist.
I mean,
you cannot
maybe. Yeah, so maybe you live in a closed time Lie curve and then they exist and then you have paradoxes all the time. But the thing is, the world we want to consider is one where it doesn't exist. So in the process function framework, it doesn't exist.
Okay.
Does that make sense?
Okay.
Yeah.
Thank you.
So this will become more clear. Like when I come to the notion of non-classicality, all of this will come back. So it's good that we spend some time discussing this. So hopefully it'll make more intuitive sense later once you think about it. Ian, were you okay with that, or did you have questions again?
No, everything is clear now. So in this,
Okay.
let me say something, and you tell me if I'm off the track. So in this process function thing, you are only keeping these extremal points of the set of conditional probabilities which satisfy logical inconsistencies.
Exactly.
So you're throwing out all the other. Yeah, I see.
Yes.
So it's a kind of
Yeah.
convexity business. Okay.
Yes. Yeah. Okay. So if this is good, then okay. So this was just like introducing the framework so that you understand what I'm saying. So I'm just giving you some definitions in some sense. It's good that we discuss. So hopefully it's smoother now. So causal inequalities. So what are causal inequalities? So these are supposed to be operational constraints from assuming a definite causal order between the labs. Okay, so assuming a global causal order. So you don't necessarily assume a concrete DAG. You don't necessarily assume a concrete causal structure between the labs, but you assume there is a DAG. Okay? It's the existence of a DAG describing what's happening across the labs. That's what causal inequalities capture. Okay, and if you violate a causal inequality, that rules out that there is a DAG. Is what it's saying. Okay. So here's an example. So it's best to introduce these things by example. So this is an example of some what's called the guess your neighbor's input inequality. Okay. So now we look at an environment and we look at two parties that are embedded in this environment. The first party receives a bit A1. It responds with a bit X1. The second party receives a bit A2, responds with a bit X2. These parties can do whatever they want to the systems they receive and they send out, okay, according to the theory they're working in. We don't know what the theory is at the moment. But now, if you ask that the theory be causal in the sense that, that you don't have loops, like you don't have things going like this, like, you like output, Alice's output goes to Bob's input and Bob's output goes to Alice's input and like simultaneously, those two things happening, that would be non-causal. And the way to see that is to think of this game where party one is supposed to guess the party two's input. So its neighbor's input. So party two received some input and party one is supposed to guess that. Okay. It doesn't have direct access to A2. The only way to access it through its input system in some sense, right? Which can talk to what the output system is the second party. And party two similarly must try to guess the first party's input, A1. Okay. Again, there's no way to access information about A1 except through its input system. Okay. So this is the game. And now if you think a little bit about it, okay, let's look at the winning probability. So the winning probability of the game is if the questions are uniformly randomly chosen, if these are bits, right? And if you sum over those probabilities where they win the game, so where x1 equals a2 and x2 equals a1, then this is the winning probability in the game. Okay, and the claim is that in a causal strategy, you cannot win this game more than half the time. Okay, the probability is half. And that's because the optimal strategy, if you just think about it for a bit, you will see that this is true. That the optimal strategy is that, okay, Alice sends A1 to Bob. So Alice just encodes her value of A1 in the outgoing system, sends it to Bob. Bob just decodes it here and reports it, right? So x2 equals A1 perfectly, no problem. But if Alice already exploited the channel to do this, then she's forced to make a uniformly random guess for what Bob's input was. Okay. So note, again, implicit in this, everything I said is that formally this corresponds to the parties only having a single round of communication in some sense. Okay. Because they only receive a system once and they send out a system once. This means that they can only do an exchange once. Okay, so that's why there's a constraint on what Alice can do for guessing Bob's input. She can at best do randomly, and this strategy will not do better than half. Okay, is that okay? Because so again, if you allowed 2 rounds, if Alice was allowed to send her input to Bob, and then Bob was allowed to send his input to Alice in a second round, then yes, they can win the game perfectly. But that's not the scenario we're in. We're in a scenario where they only receive systems once, like an input system and an output system, and there's a causal order between the input and the output for each part. Okay, under that assumption, they cannot win more than half the time. Okay, so this is an example of a causal inequality. And it's interesting, the reason people study these things is because if you were looking at what I described as the process matrix framework, then you can generate correlations which violate this inequality. In particular, you can write down an environment, a process matrix, which allows, by sending and receiving qubits, to do better than half. Okay, I don't remember the exact numbers, but yeah, you can look it up, and it's in this paper. Okay, so you can violate the inequality with process matrix correlations. So that's one reason why people care about this. Now you might ask, okay, in the original OCB paper and the Oreshkov Costa Bruckner paper, there is there's a conjecture, or there's an intuition in that paper, which is that we have causal inequality violations because of process matrices, because they allow these weird superpositions of causal orders. And so maybe if we go to the diagonal limit of the framework where parties only receive and send classical systems, we will recover causality. We will not have causal inequality violations. And that is true in the bipartite case. If you just have two parties, and if you restrict them to just receive and send classical systems, then in the most general case, you cannot have causal inequality violations. Parties will be causal. Okay, so this is true. This intuition is recovered that the diagonal limit recovers, causality is recovered for the bipartite case, but it fails in the general case. So if you have three parties or more, then you can violate these inequalities. Okay, and you can violate them using classical examples. So in particular, the first example was what I'm calling here the BFW, Baumiller-Fix-Wolf process. That's in this paper, the second one here. This is an example of a classical process, but it's a classical process that's not in the process function framework. So it's not a convex mixture of process functions. Okay, the second one, we're calling it AFBW. It's just after the names of the guys who came up with it. So it's the Araujo, Fakes, Baumiller-Wolf. That's in this paper, and this is a classical deterministic process. So it's a process function. So the second one is a process function, and this also violates a causal inequality. So you have a causal inequality violation not only in the process matrix framework, you have it in the classical process framework, and you also have it in the process function framework. Okay, so with three parties, like the intuition that in the diagonal limit you recover causality breaks down. That's kind of what I'm trying to get at. And okay, so this is again, I'll not go into details of this, but this is a tripartite causal inequality that shows that you have process function violations of causal inequalities. So again, three-party game, they receive bits, send out bits. There's some rule for winning the game, and under causal strategies, you only do 3/4. Like that's the best you can do. And using a process function, a classical deterministic channel from outputs to the inputs of the labs, you can violate this perfectly, maximally. So you can achieve value 1. Okay, so that's why this is the classical example that's in this paper. And the concrete the form that this function takes. So here's what it looks like. So this is how the input of party 1 depends on the outputs of the remaining parties. So it's the same form for the other parties also. So output 2 of the second party, or 2 bars. So you flip the bit of the second party and take the product with the bit of the third party, and that describes the input bit of the first party. Okay, so the important thing to note here is that the way this, if you look at the causal structure of this function, this is actually each party is in the causal future of the other 2 parties. So you cannot kind of give a causal account of this process function. Okay, so there's no global causal order for this. In some sense, it maximally violates causal order. Okay, because every party is in the future of the other parties. Okay. And so, yeah, so that was just to describe an example. And the moral of the story, the reason I did this detour into causal inequalities is to point out that there's this very rigorous sense in which causal inequality violations do not require non-classical resources. You can just process functions and violate causal inequality. Okay, so how do we know? Yeah.
Sorry for the interruption. There was a small question for me, which was, is there a device-independent sort of operational way, like you're describing, to separate operational, what were they called? These functions and classical functions. What were they called? Sorry, I forgot the names. There was the process function
process
and
functions.
Not the matrix. Process function and the classical one, at the convex formation. The general one, sorry, not the convex formation. I should have forgot. Is there a device independent way of separating them?
say that again. Like, what do you mean by device independent thing separating? What are the two objects? So one object is a process function, and you want to separate it from which other object?
So there was the process function, and then there was the classical process framework,
like an
right?
arbitrary function, you mean, or?
Yeah, but wait. Okay.
Process
So
functions
there were,
or mixtures of process functions?
yeah. So what were the three things? There was the process matrix, right? And then the classical restriction of that was what? What was it called? Process function.
There were two restrictions. This is the process matrix framework. This is the classical process framework, and this is the process function framework.
Yeah. So the distinction between the last two, is there an operational way to distinguish the last two? In the sense
that's actually that's actually one of the main results of our paper. So I'll come to that at the end of the talk.
Okay.
An operational way to distinguish them.
I see.
Okay, that'll come. Just hold your breath for a bit. Okay, so yeah. Okay, so causal inequality violations do not require non-classical resources. So the question is, so again, I'm at the start of my talk now. So if I hope you're all fresh and paying attention. So when is a non-causal correlation also non-classical? That's the question you're asking. And our answer is this notion that we call antinomicity. And now I might go a bit fast because I will probably not prove results, but I will state definitions and combine it with what we've discussed so far to express what this idea is. Okay, so we're trying to propose a notion of classicality for correlations that can be generated in this general operational paradigm, where you don't necessarily assume a global causal order. And the notion of classicality, we call it deterministic consistency. This is the long name, and the short name that I've chosen for it is nomicity now. I actually came up with antinomicity first, and then I was like, well, it makes no sense to call something non-antinomic. It's just anti-antinomic. Let's just call it nomic. So that's the motivation for the name nomicity. Okay. In philosophy, it has a different meaning, but it has a similar meaning, like something that's normal, like not out of the ordinary kind of thing. But anyway, it's not a very widely used word, so I thought it was a good word to pick for a technical notion. And what is this notion? This notion says that a multipartite correlation is nomic if and only if it can be achieved in the process function framework. So since I've already introduced the process function framework, I'm not obviously going to repeat that, but it just means that given a correlation, you can write down a decomposition of this form. Okay, that you can express it in the process function form, where this conditional distribution is not arbitrary; it's a convex mixture of process functions. Okay. That's the constraint, and yeah, for arbitrary interventions here, it should give me sensible probabilities. Now, the key thing to note in this expression is that if your environment was non-signaling, and the way to model a non-signaling environment is to essentially, when you say environment is non-signaling, that's saying that this P of I given O has no dependence on O, that the inputs of the parties are not dependent on their outputs. They're autonomous from the outputs, okay? Because the outputs are the only way to signal to other parties in this framework. Okay, so if you don't send any outputs, for example, if the parties discard their outputs, right, then you're basically back to a Bell scenario. And formally in this expression, that corresponds to putting this P of I given O, replacing that by just P of I, okay, and coarse graining over O. You sum over O. And then you will see that it basically it gives you a Bell local model in that picture. Okay, if I sum over O, this is P of xk given ak, ik, and then some distribution over all of the ik's. Okay, this is formally like a locally causal decomposition of a correlation. Is it clear that if the environment is non-signaling, this will reduce to Bell locality, this nomicity? Like, if there are questions, please ask, because I think it's important.
Clear to me.
Okay. If it's clear, then I can go on and build on top of this. Okay, so when I say non-classicality in the presence of indefinite causal order or antinomicity, what we will mean by this is the failure of this notion of classicality, which is nomicity, which is achieving a correlation using the process function framework. If you cannot do that, then we call the correlation antinomic. Okay, so intuitively, so now let's give it more of a physical spin. Intuitively, antinomicity is the property that the classical environment, so if you were to try to explain the correlation using a classical channel from the outputs of the parties to their inputs, then this classical environment must actually allow for hidden sort of logical contradictions. in order to be able to reproduce the correlations. Okay, so it's like it may be that in the support of your conditional distribution from the outputs to the inputs, there are things that are not process functions, and you necessarily have to have those things in order to explain the correlations. So it's a bit like I mix the the grandfather antinomy with probability half with the information antinomy with probability half, and then I get no antinomies on average. But it's still the case that underlying you're hiding the antinomies. Okay, so it's kind of a notion of, another way to think of it is like in the Bell case, like when people say non-locality in the Bohmian picture, often one way to think of non-locality is that it's actually some hidden superluminal influence that's going on between the parties, but it makes no operational difference because the influences get washed out because you just mix over, complementary sort of underlying descriptions to get an overall non-signaling description. So like the rigorous way to think of it is if you write down a PR box, you can always express it as a mixture of two signaling boxes, deterministically signaling boxes, and they only differ by like a bit flip. And when you average them, there's no signaling. So you can do this exercise. You can decompose a PR box into two signaling vertices, which mix to give you the PR box. And that's effectively like one way to see the non-classicality of the PR box is that it requires a decomposition over vertices that are signaling. You cannot write down a non-signaling decomposition of the PR box because if you did, you would be inside the Bell polyton. Okay, so again, I'm drawing an analogy. It's more rigorous than just an analogy, but like for now, I'm just trying to say that antinomicity is in some sense an extension of Bell non-locality to a situation where you don't have a definite causal order. Okay, and now let's try to make it a bit more rigorous. So correlation sets. So just an analogy with Bell scenarios, I'll call a general correlational scenario. I'll denote it by a tuple of three numbers: the number of parties n, the number of settings per party m, and the number of outcomes per setting d. Okay, so these are the settings, these are the outcomes, and there's only two constraints: that the probabilities are non-negative and they're normalized. Okay, so you have the full hypercube of like distributions, like everything is allowed in this scenario. So note that there is no non-signaling constraint because the parties can exchange systems. So in general, I cannot put down another equality constraint like non-signaling here. Okay, and I have to work without.
Sorry, Ravi.
Yeah.
Could you explain what NMD were again? I kind of missed that. Sorry.
N is the number of parties, so the number of labs. M is the number of values that each setting takes. So AK will take m possible values, and D is the number of outcomes for each setting, the number of values that XK will take for each AK.
Okay, thanks. Sorry.
Yeah. So it's like in Bell scenarios also some notations use this, like a lot of people write them like this traditionally.
Right.
Okay.
Sorry, yeah.
No worries. It's good that it's clear. Okay, so the important thing is that there's no non-signaling constraint here, okay, because the parties can explicitly signal in this framework. In fact, they can signal non-causally. So we have to kind of distinguish classical instances of non-causal signaling from quantum instances or non-classical instances. Okay, so we defined 4 sets of correlations in this framework, in this correlation scenario. So the first is the nomic set. This is our classical set. So it's called DC here because it comes from the original name, deterministic consistency. So these are things you can do with process functions. Okay. Then we define another set that we call probabilistically consistent correlations. These are the ones you can achieve via, you can say, diagonal process matrices. So Atul, earlier you asked me about the distinction, operational way of distinguishing between these two things, and that will essentially be a gap between these two sets of correlations. Okay, it'll come up. Okay. And then the third is this quantum process correlations, which is things you can do with quantum process matrices, okay, if they were exchanging quantum systems. And the final set, this actually doesn't fit the description, like at least I don't know of a theory that achieves this set. We call it quasi-consistent correlations. And this is just to kind of point out that this is the full set of correlations, so like arbitrary distributions. And if you allow arbitrary classical channels, like you don't care about paradoxes, you can reproduce anything. Okay, if you allow for time travel paradoxes, you can do anything. Okay, that's basically what this set is kind of telling you. QC is everything you can do. Okay, it's the full set of correlations. And our main sort of the highlight device independent result that we have, there's other results which are more about causal models and vertices. But they kind of feed into this hierarchy, is that there's a strict separation between these correlation sets. Namely, the nomic set is contained strictly inside what's called the probabilistically consistent set of correlations, which is strictly inside the quantum process set, which is strictly inside the full set of correlations. So again, we show that there are correlations, there are distributions for n parties that are unachievable even if the parties were sharing quantum systems. So in some sense, this is the analog of like, the PR analog of the PR box, like something that you cannot do with quantum stuff. Okay, so it puts bounds on what you can do even with process matrices. Okay,
Ravi, I have a dumb question. So in the last set that you described in the previous slide, when you say achievable via arbitrary classical channels, is it the environment being arbitrary classical channel without any constraint on?
Yes, arbitrary distribution P of I given O.
I see. So does it make sense?
No logical consistency. I don't put any logical consistency assumption in that case.
Right. So does it mean that arbitrary quantum channels are not going to be much more powerful than arbitrary classical channels if you're not imposing those constraints?
The thing is, quantum channels are not arbitrary. Like not all quantum channels form valid process matrices. So like they're a strict subset of possible quantum channels from outputs to inputs of the parties.
Right, but I thought the process matrix was achieved by, like basically was defined essentially by requiring that the probabilities are consistent, right? There was this additional constraint.
Yes.
So if you do not put that constraint and otherwise allow the description to be quantum, does that change anything for QC?
Yeah, then you can do anything. If you don't require logical consistency, the process matrix can be arbitrary. If it's a quasi process matrix, so to speak, then you can achieve whatever correlation you want. Because you can
also achieve those with the diagonal. But you could achieve the same with the diagonal process matrix.
Exactly. You don't even need to go to look at like relaxations of the process matrix. Yeah.
I see. That's what I was saying. Okay. Thank you.
So the hierarchy collapses is what I'm trying to say. If you relax logical consistency, there's no gaps.
Right.
Like anything goes. Like is what I'm saying. Like, there's no laws in the world. Not even basic lack of logical contradictions in your physical theory. So you can do anything.
Okay, sure.
Yeah.
Okay. Thank you.
So it's just like in a Bell scenario. Imagine a Bell scenario where you have the non-signaling constraint. If you relax the non-signaling constraints, there's no gap between classical, quantum, and whatever. Like it's everything. You can achieve any causal signaling correlations using classical systems. You don't need quantum systems for that.
Right.
You see, in Bell scenarios. So it's the same thing here, except like we're talking about logical consistency rather than non-signaling. Yeah.
Thank you.
Okay, so this is the most important theorem of the paper. I've stated it in a sort of a colloquial way, just so it's easily understood. The more detailed statement you can find in the paper. The statement here is that a deterministic correlation. So again, if I use the word deterministic correlation, it means a function from the settings of the parties to the outcomes. Okay, so they give deterministically some set of outcomes if they receive some set of settings. So a deterministic correlation can be realized by a process matrix. So there's a process matrix strategy for achieving some deterministic correlation. If and only if, it can also be realized by a process function. So you can only do it quantumly if you can do it classically. This is what this theorem is saying. Okay, a deterministic correlation, not an arbitrary probabilistic one, but one which is like a function from settings to outcomes. Okay. I will give it a moment to sink in, but maybe one way to kind of think of it is as a generalization of the Bell case. So if you think of the non-signaling Bell case, okay, again, go back to the Bell scenario, think of deterministic correlations. When I say deterministic correlations, it's a function from settings to outcomes. And if I require non-signaling on top of it, it's just local functions, it's choices of local functions. Okay. And you can only do them quantumly if you can do them classically. So, and basically that's the Bell polytope. Those are vertices of the Bell polytope. The only deterministic non-signaling correlations you can achieve in a Bell scenario are the ones that are the classical ones, which are vertices of the Bell polytope. This is a generalization of that observation to the case of a situation where you're working with process matrices, where there is an explicit signaling. But here still it's true that if you can do something deterministically, like from a function from settings to outcomes, using a process matrix, then you should be able to do it with a process function. Basically, process matrices don't give you any more power than process functions when it comes to computing deterministic functions from settings to outcomes. Okay, that's the physical kind of content of this theorem. Yeah. So
can I ask a question,
yeah.
Ravi?
Yeah.
So to go back to the parallel with the Bell case. So in the Bell case, you don't have, I mean, a distinction between this diagonal process matrix and process function, right?
Yeah, in the Bell case, you just have quantum states. You don't have. I mean, your process matrices are quantum states, right? There's no.
Right.
Yeah.
Right, but you have these two, like this process. There are two like kind of classical settings in your theory, right?
Mm-hmm.
And in the Bell case, I cannot see any difference between them.
There is no difference, because if you discard, as I said, like if you discard these outputs here, it doesn't matter what the P of I given O I took. If I discard the outputs, I recover like everything is the same. Well, okay. See?
Yeah. Can I ask a second question? Well,
yes.
So in this chain of inclusions that are strict that you presented, do these sets have like non-empty interior in the set of correlations, or I mean, do they have the same dimension, or?
They're in the same dimension because there's no equality constraints. So. Like I said, there's no non-signaling, nothing.
I see. So everything is about inequalities. Okay.
It's full dimensional. Like it's the full. Yeah. Yeah.
Thanks.
Is this okay? So the important observation here is a corollary of this, which is that if you can prove that a deterministic correlation is unachievable by a process function, then that implies that it's unachievable by a process matrix. Basically, it's an easy way to show that certain correlations are just outside the quantum set. Okay, you just show that they're outside the classical set as long as they're deterministic, and then you know they're outside the quantum set. Okay, so this is what we leverage basically to prove our strict inclusions in some sense. Okay. Okay, so here's the logic. So for the first case, the fact that the quantum process correlations are a strict subset of the full set of correlation. So first we recall the theorem, like, you can do it with a process matrix. That means you can do it with a process function. In the bipartite case, we know that if you ask for a perfect correlation in the guess your neighbor's input game, where each party guesses the other's input perfectly, we know that you cannot achieve it using any process function. Because in the bipartite case, in the diagonal limit, you don't have causal inequality violations. All the process functions are causal. So you cannot win that game more than half the time. Okay, so you know that in the bipartite case, you cannot do it classically with process functions. That means that you cannot achieve it quantumly. Like there's no process matrix strategy that will win that game perfectly. Okay, so it tells you that you cannot achieve this particular point in the space of distributions using quantum strategies. It doesn't put a bound on how close you can get, but it tells you no matter what you do, you will not achieve that point. Okay, so it excludes points rather than volumes, basically, like this kind of argumentation. Okay, to exclude volumes, you need to prove things like Sillson's bounds and stuff, which is what we don't do in this paper. So that's the first one. The second one is much simpler, which is that the set of probabilistically consistent correlations is inside the process matrix ones. So the classical process stuff is inside the process matrix. So this follows just from the bipartite case, because the distinction between DC and PC collapses in the bipartite case, because you don't have any examples of classical violations of causal inequalities. So and we know that they're violated by process matrices. So that kind of gives. So this one comes for free. This we don't have to do any work. That's just based on previous. Actually, even in effect, both of these kind of come for free once we have the theorem. Okay, it's the third one. So this goes back to this was Atul's question of like, is there an operational way to distinguish between these two sets of correlations? And this is kind of our answer to that. So if you come up, if you play this game, so we call it the guess your neighbor's input or not game, where there are three parties. Each party is supposed to guess its neighbor's input. So X1 is supposed to guess the input of A3. So party 1 guesses the input of 3, 2 guesses the input of 1, and 3 guesses the input of 2. So they're in a cycle. Okay. Or each party guesses the bit flip of its neighbor's input. Okay. So so one of these two conditions should be true. in order for them to win the game. And if that's what you require, then the winning condition, the winning probability looks like this, right? Like, so you assume uniform choice of the settings, and then you average over those outcomes which satisfy your constraints. And so then we show that there are bounds on this number, on this winning probability. So causally, you cannot win this game more than half the time. So you cannot do better than random. The argument is similar to the guess your neighbor's input case. Classically, so by classical, I mean the nomic case, the process function case. We proved that there's a bound on this number and it cannot be more than 5/8. Okay, and actually, like, this bound is achieved by this thing called the Lugano process function, or the AFBW process. Okay, so this is in DC. Okay, and then if you go beyond the classical case, if you allow for antinomicity, then you can actually go all the way to 1 using this example of a process like the BFW, Baumiller-Fakes-Wolf process. Okay, so this is the PC. So there's a strict gap between these two sets. Okay, and in fact, like, this set already achieves the maximum, so you don't even need to go to the full process matrices to achieve the maximum for this case. Okay. Okay, so this brings me to the end of the talk. So the first thing I sort of
Sorry. Before you start, what was the last comment you made? You don't even have to go to the full power of process.
Yeah. So this set is, I said this set is PC, right? The set is not QP. QP was quantum process. This, right? So I'm saying already in this set you're
already maximize
maximum violation. Yeah. So this inequality is not useful in some sense for seeing the gap between
PC and PC.
Is what I'm saying. Yeah.
Thank you.
Okay, but it does what I wanted it to do, which is to give the gap between these two guys. Okay.
Right.
So it gives an operational distinction. Okay.
Right.
Okay. Good. So yeah. Question. Okay. If not, I will maybe just summarize, and then I can take more questions if there are any. So, okay, so the first thing was, not every causal inequality violation is a witness of non-classicality. I spent like most of the talk, I think, at the beginning trying to motivate this. Second is this proposal that we made of if you're in a situation with indefinite causal order, it makes sense to us that antinomicity is a good notion of non-classicality, because essentially, like, it's also because of that theorem, which kind of shows close parallels with Bell. Okay. And then we show that, okay, this is actually a useful notion to define, because it allows us to prove strict separations between different sets of correlations. And the most important thing, I guess, like conceptually important thing, is that we didn't make any assumption about network structure here. We only made an assumption about the theory, that the theory must give sensible probabilities, which was logical consistency. And so in particular, we didn't even make the assumption that the network structure is kind of some sort of DAG, like, which is what you would do to derive a causal inequality. Right. So we even lifted that assumption in order to write down our inequalities. And so when you violate these inequalities, this is just saying that, okay, like, if you were to try to give a classical environment that does that reproduces this, there's no way you can do it in a world without logical contradictions. You will necessarily have to live in a world which has fundamental logical contradictions in order to see these antinomic correlations. Okay. And this is like your usual picture of Bell local, quantum non-signaling, and non-signaling correlations. So Bell inequalities separate Bell local from the rest of non-signaling correlations. This is our picture. So this is what we've updated it to. Causal inequalities, they separate causal correlations from the rest of the correlations. So causal correlations contain non-signaling correlations in particular, right? So these are all the signaling correlations. And then process function correlations contain causal correlations. These are the nomic set. This is our classical set. And then everything outside is antinomic for us. Okay, so antinomicity constraints, they separate process function correlations from everything else, okay, including process matrix stuff. So I will end there. This is the paper if you want to check. I can discuss open questions if you want later, but I can take questions. Thank you.
Hi, Ravi. So if you go back to the last, this kind of structure, that slide of yours, and the previous one in the Bell scenario, So is the thing is that in case of Bell scenario, we know that this quantum no signaling correlations, the extremal points of these quantum no signaling correlations are PR box kind of structures. So do you
Well,
have
of non-signaling correlations.
non-signaling correlations, right? So what are these in the process matrix framework? What are these extremal points?
Of the general set,
Yeah,
like of antinomic
yeah,
set.
yeah,
Yeah.
exactly.
So for example, in the single party case, the examples I showed you were kind of the extremal points, like where you just do deterministic things that give you paradoxical. Well, no. Sorry, actually, those are not, because those give you just paradoxical probabilities. But the extremal points are essentially, so if you look at these constraints, right, these ones, right. So the extremal points of this set are just all deterministic distributions from settings to outcomes, right? Those are all the extremal points. It's like extremal points of the non-signaling polytopic Bell scenario. That's what these guys are, right? If I write down an arbitrary distribution that's deterministic from settings to outcomes, that's an extremal point of the full space of distribution. So it's not so interesting. Like, it's not like you don't need a theorem to say that these are extremal. They are just extremal by convexity. Yeah. The interesting thing is actually which of these extremal points, the deterministic ones, are also extremal points of the nomic polytope of this correlation set. Okay, that's the interesting thing, because not all of them are actually achievable under a logically consistent kind of theory. Okay, not all of them are achievable under achievable with process functions. So not all of the vertices of this are achievable with process functions. Only some of them are. And if you identify which vertices they are, that gives you a description of the nomic polytope. And actually, like an open problem, I didn't come to it, but maybe this is a good time, is to try to characterize the nomic polytope in this scenario, the one that we were looking at. 3 parties, 2 settings per party, and 2 outcomes per setting. Okay. So if you look at the longer paper, we've characterized vertices of the full polytope, and then we've isolated the class of vertices which in which the nomic set falls. Like the nomic set of vertices comes from a specific class, and we identify that. But we only have some we don't have necessary and sufficient conditions for identifying which ones exactly are the nomic ones. We have some sufficient conditions, some ways of ruling out, but we don't have a complete characterization, for example, of the nomic polytope.
Yeah. So
help?
my second question is the third point that you have mentioned. My second question was about to be the third point, the trichel bound.
This one, yeah. Yes. So you can ask for
No, I am saying that your comments and insight on that, because I was about to ask this question, whether there is kind of a bound on this process matrix correlation framework.
There is bounds, right? Like, so the thing is that you already, like, our results kind of tell you that there must be a bound. We don't actually prove the bound, but what we do is we show that certain points in the space of correlations are unachievable with process matrices, right? We don't say that how far you can go in achieving these points. We just know you cannot reach those points. Okay, so that's what we do. But if you look at this paper, a recent paper by Liu and Kiribella, they have developed techniques for bounding causal inequality violations with process matrices. So in particular, they prove like bounds on the guess your neighbor's input and guess your something called lazy guess your neighbor's input, using techniques that they develop in this paper. So I would recommend reading this paper if you're interested in ways of obtaining bounds on causal inequality violations. The thing is that I think the same technique should apply to the antinomicity case, because something I forgot to say was that every time you see antinomicity, it implies a causal inequality violation, but not conversely. So you can have causal inequality violations without having antinomicity. But every time you see antinomicity, there must be causal. So these techniques should be useful for antinomicity also, is what I wanted to say. Yeah.
If I am correctly saying that even in case of the Bell scenario, so if you look into the Bell violation, so even the no signaling, so the PR box type of correlation will maximum violation for, and any no signaling correlation, if you any signaling correlation if you take by hand, it will cannot go reach beyond the maximum violation. So there is no way to distinguish with the help of this Bell inequality violation from a signaling correlation to this PR box kind of correlation.
Yes.
So same thing happens. Same thing happens over here in the causal inequality.
So the same thing in what's the analogy in your mind? So I see that
causal
if you relax.
Causal inequality violations, in case of causal inequality violations that you are talking about, if I am putting it correctly,
maybe we're kind of past the 1.5 hour mark.
Okay.
So maybe
I
don't know, maybe at least time to speak, or maybe if you want to
answer the question.
Up to you guys. I can try to answer if you want.
Okay, so at least let's thank Ravi for the talk. And
Thank you.
yeah, maybe Ravi, I'll stop the recording. Maybe you can chat if you want, Ravi. If you have a few minutes, maybe you can clarify the questions. I'll stop the recording though.
Okay. Yeah. I should eat soon, but I can answer that last question.